Okay, so welcome again to the Galaxy and Cosmology Stars and Planets seminar. A quick reminder that we, for asking questions, basically use the raise hand feature, as we have done for the past number of weeks. And also please sign up to the one-on-one sessions for the speakers if you haven't done so already. It's always a good opportunity to ask many more questions there. So without further ado, I will introduce our first speaker this morning is Jennifer Yee. She did her PhD at Ohio State University and came to the CfA as a Sargent Fellow in 2013. Later, she was hired as a federal staff at the SAO, and her research focuses on microlensing for which to discover and characterize planets. So I will hand over to Jennifer.
Okay, hello everyone. Before I launch into talk slides, I want to start by taking a poll, just so that we can understand where we're starting from. And so the poll has only one question: approximately how many planets have been found by microlensing? And so your choices are 30, 60, or 100. So please take a minute to fill out the poll. Whatever answer you give is fine. There is a right answer, of course, but the poll is anonymous, so it doesn't really matter. And the primary purpose is just to take a kind of pulse and understand where we're starting at the beginning of the talk. Okay, so it looks like 14 out of 18 of you have voted, and so since the rest of us, I think, are co-hosts, that seems pretty good. So I'm going to end the polling now and share the results. And so based on this poll, about 40% of you think that there are about 30 microlensing planets, 53% think there are 60 planets, and one of you, or 7%, thinks there's about 100 microlensing planets. And so now I'm going to share my screen and provide you with the answer. So can you see my slides now? Okay, good. All right, so we have a question. The answer to this question is that there are about 100 microlensing planets. And so even though there's 100 planets, I think many of you underestimated the number of planets. And I think there are two primary reasons why people tend to underestimate the number of microlensing planets. The first reason is that a lot of the emphasis lately has been on transiting planets. And one of the major observables with transiting planets is period. And period is not something we measure with microlensing. And so this is just a standard canned plot that shows up a lot from the Exoplanet Archive. It shows planet mass as a function of period, and it shows all of the known planets with measured periods. But because we don't measure that typically for microlensing, there are very few microlensing planets on here. Those are the purple triangles. And just to help you out there, because there aren't so many of them, I've made the purple triangles extra big. And so there's only 8 microlensing planets that show up on this plot. And so your impression, if you are used to looking at plots of planets as a function of period, is your impression will be that there aren't very many microlensing planets because we don't measure periods. The other reason that you might underestimate the number of microlensing planets is that the situation has changed very rapidly in the past few years. And so this is a plot showing the number of microlensing planets published each year, and that's the magenta plot. And then the black is the cumulative distribution of microlensing planets over time, and that corresponds to the right-hand axis. And so what you see from this plot is that there are about over 100 microlensing planets now, but just 2 years ago, there were only 70. And as recently as 2015, there were only about 30 microlensing planets. And a large reason for this rapid increase in microlensing planet detections is the Korea Microlensing Telescope Network. And so to understand the context of KMTNet, we need to understand where we were before KMTNet. And so prior to KMTNet, the major result on the planet population as measured by microlensing, this major result came from Suzuki et al. 2016, which used the MOAA survey to measure the mass ratio distribution of planets. And so the black histogram here on the bottom shows there are 23 detected planets in their sample. And it shows that that distribution is reasonably flat as a function of log mass ratio. And the fact that smaller planets are harder to find implies that a flat distribution, once you've corrected it for detection efficiency, means that there are many smaller planets than there are larger planets. And so when you correct the black histogram, you get the red histogram, which shows that basic effect. There are many smaller mass ratio planets than larger mass ratio planets. And at the top of this diagram, I've indicated an Earth mass ratio, a Neptune mass ratio, and a Jupiter mass ratio. So the two major things that we know about microlensing planets is that there are more Neptunes than there are Jupiters, and that there are a fair number of giant planets at microlensing-like separations, which is separations of a few AU. However, one of the surprising results that came from the Suzuki study is the suggestion that there's actually a break in the mass ratio distribution. And so they had no detections of planets smaller than about a Neptune mass ratio. And based on this, they found that the distribution, once corrected for detection efficiency, was best fit by a broken power law. And so the gray, though, shows that there are very large uncertainties in this power law. In particular, there's a range of places where that break might occur around or above a Neptune mass ratio. But the slope of that power law is very uncertain for planets that are smaller than a Neptune mass ratio. So it seems that there should be fewer super Earths than there are Neptunes, but how many fewer and whether or not there's like actually none is very uncertain. And so the super Earth regime is really where we want to be finding planets and making detections so that we can characterize the mass ratio distribution for the smaller planets. And so the key for doing that is to understand that the time scale is proportional to the square root of the mass of the object. So the time scale of a planetary perturbation for a Jupiter mass planet is typically about 1 day. And so if you want to find super Earths, then you're looking at time scales that are about 5 hours. And that's where the real power of KMTNet comes in. So KMTNet is the largest ground-based microlensing survey, and it has 3 telescopes, one in South Africa, one in Australia, and one in Chile. And what that allows you to do is that it allows KMTNet to get continuous coverage of the night sky. In addition, KMTNet has a really large camera. So the field of view of this camera is 2 degrees on a side. And the little inset on the right shows you just how many stars are observed in each pointing of this camera. And so with this large camera, KMTNet can cover about 100 square degrees in the bulge at a very high cadence. And so this is a plot of the KMTNet fields in galactic coordinates. So the plane runs horizontally through this plot, and the fields are color-coded by their cadence. And so the fields we care most about in this context are the purple fields. Those purple fields are each observed at a cadence of once per half an hour. And each of those fields actually consists of 2 offset pointings. And so the effective cadence in those fields for most stars is once per 15 minutes. And so with a 15-minute cadence, you can get many points in a 5-hour perturbation and be able to characterize these signals from super Earths. So as an example, here is one such microlensing event observed by KMTNet. The overall event lasts for about over 100 days, and that's dominated by the stellar event. But at the very peak of this, there's some very short timescale perturbation due to the planet. And this event also has Spitzer data, which are in black, but that's the subject of another talk. For now, let's focus on this planetary perturbation. If I blow that one up, you can see the real power of KMTNet. If you only had the data from South Africa, the blue data, then you would almost entirely have missed this planetary perturbation. And if you only had the orange data from Chile, you would have maybe 1 point on the perturbation, and you'd be like, is that point real, or is that just a weird outlier due to like cosmic rays or something? But with having these 3 sites, you can see that we have several points over this perturbation, and it's clearly detected and well characterized. And so here's another such event, longer time scale due to the stellar event, little blip due to a planet, which again is characterized very well by KMTNet data from 3 different sites. And so in this case, all 3 sites see the perturbation. And this perturbation is 12 hours long and also corresponds to a super Earth like planet, like mass ratio. Then there's a third one, same deal, long time scale event, little blip on the side, What's different about this event is it's actually in a 2.5-hour KMTNet field. And so there's only 3 points over the major perturbation. This event was analyzed by Weicheng Zhang. And what he found, though, is that even when you eliminate the follow-up data, which characterize the perturbation very well, you can actually find and you can detect and characterize this planet with KMTNet data alone. And that's due in part to the fact that there are several points that go below the point lens curve. So the dashed line is what you would expect if there's no planet. And there are several KMTNet points that lie below that curve, which contribute to the detection of the planet in these data. And I should mention that Weicheng is a student at Tsinghua University who's working with Shuda Mao, and he's going to be finishing up within the next year or so. And so he will be applying for postdocs in the fall. And so to place these planets in context, we should look at all of the microlensing planets together. And so this is a plot of all of those planets, mass ratio as a function of separation. So the planets are, the distribution is centered at 1 Einstein radius. Planets in gray are ones with ambiguous solutions. But you could see from this plot that planets, the microlensing planets span several orders of magnitude in mass ratio. Of course, the ones we're interested in are the smallest ones, so let's blow that up. Now, unfortunately, we've switched from gray to red for the ambiguous solutions, but hopefully it's still reasonably clear. What I've added now, though, are 2 horizontal lines. The dashed gray line and the solid gray line show sort of the range of locations for that break in the mass ratio function. And so the key thing is that those 3 planets that I showed you are the 3 smallest mass ratio microlensing planets, and they're all below this break in the mass ratio function. And in addition to these 3 planets, there are actually several other planets and planet candidates that have been discovered, most of them by Weicheng Zhang, including one that was just out on the archive last week. And so I haven't had time to add it to this plot yet. But he's really, he's sort of a planet finding machine in terms of finding these small mass ratio planets. So with these planets, first, it's clear that we're going to be able to measure the mass ratio distribution of planets in the super Earth regime and maybe down to Earth using KMTNet, because now we have actual detections below this supposed break in the mass ratio function. The other thing that you can see from this plot is that the points are reasonably evenly distributed between the vertical dashed black lines. And those reflect something about the detection efficiency. But if they're evenly distributed, that implies, again, that small planets, there are more small planets than there are large planets. And there doesn't really seem to be a break in how these planets are distributed as a function of mass ratio. They're just pretty even all the way down. And so that suggests that as we find more of these super Earths and start characterizing this population, that the break may actually go away. And so that there may actually be more super Earths than Neptunes, but that requires a full statistical analysis to say for certain. But right now we have a suggestion of that. Okay. Then the other major result that has come out of microlensing is the suggestion that there's a large population of free-floating planets. And so this is done based on the timescale distribution of single lens events. And so again, timescale is proportional to the square root of the mass. And so events with timescales of less than 1 day could correspond to planetary events. And so by measuring the timescale distribution of microlensing events, we can characterize the free-floating planet population. And so this is that timescale distribution as measured by Ogle. That's the black distribution. And the interesting thing about this black distribution is it is inconsistent with the red dashed line. The red dashed line was an earlier result from the MOAA survey from Somayeh et al. 2011 that measured in excess of 1 day timescale events and led to the suggestion that there were 2 free-floating Jupiter mass planets per star. And so with this Ogle data, the 2 free-floating Jupiter mass planets per star has gone away. However, in Ogle, they do measure in excess of events with timescales less than half a day. This work was done by Ziemek Moroz, who did his PhD with the Ogle Group in Warsaw, Poland. He's now a postdoc at Caltech working with Sri Kulkarni. But what's interesting about this is that he found an excess of those shorter timescale events, and he's very conservative about what he says about it. He says that excess is consistent, would be consistent with a population of free-floating super-Earths. And so there's a suggestion from here that even though the free-floating Jupiters have gone away, there may still be a population of free-floating super-Earth planets that can be detected with microlensing. However, the time scale of a microlensing event is not one-to-one with mass. It's degenerate with several other properties. And so as a result, a timescale distribution analysis is a statistical characterization of the population, but any given short timescale event could be due to something with a weird proper motion instead. But Ziemek Moroz has actually made a major advance in the study of free-floating planets with microlensing by finding and characterizing events with finite source effects. And so this is a timescale, a very short timescale microlensing event. It's got a timescale of only 7 hours, but it has a more rounded shape due to this finite source effect, which means that in addition to the timescale, we also measure the Einstein radius of the event, which is 9 microarcseconds. So typically for a stellar lens, the Einstein radius is 0.5 or 1 milliarcseconds. And so this is 2 orders of magnitude smaller than that, indicating that this is a strong candidate for a planetary mass lens. And so being able to measure the Einstein timescale is much better than being able to measure, being able to measure the Einstein radius, theta e, is much better than just measuring a short timescale, TE. The mass of any given lens is equal to theta e squared divided by kappa, which is a constant divided by the parallax. But because theta e is equal to TE, the timescale times the proper motion, a short timescale event can always just have a really weird proper motion, and instead of having a very small lens. But if you measure theta e instead, you get rid of this ambiguity due to the proper motion distribution. And so these events with theta e are a much more powerful probe of free-floating planets. And that's the reason why we can identify individual candidates. So Ziemek Moroz has found several of these, in fact. This one is quite striking because it has a timescale of only 41 minutes and an Einstein radius of 4.4 microarcseconds. We've also found such objects directly in the KMTNet data. Here's an example of one, timescale of 7 hours, Einstein radius of 4.8 microarcseconds. And now you might be thinking, why are we talking about timescales of 7 hours when the x-axis of this plot clearly shows that these events have a apparent duration of almost a day? And the reason for that is that the finite source effects, in addition to being a better measurement than just Einstein timescale, the finite source effects mean that the characteristic timescale of these events is set not by the Einstein timescale, but rather by the source crossing time. And so what that means is that the duration of the event is no longer proportional to the mass of the planet. It's independent of the mass of the planet. It's still very short because the Einstein crossing times for these objects are typically only about a day. But it means that we can detect much smaller planets more clearly in these events, because even though the time scale is decreasing with planet mass, or the Einstein time scale is decreasing with planet mass, the observed apparent time scale of the event is staying relatively fixed. And so with KMTNet, we've undertaken a study to search for these finite source events in order to characterize the Einstein radius distribution and probe the free-floating planet population. And so here's another event, basically the same properties, but it was discovered in this specific targeted search rather than by individual personal inspection. And this is the Einstein radius distribution measured for the 2019 KMTNet season. And so this is a preliminary measurement of that distribution. We're planning to extend it over more seasons of KMTNet data. But what you can see from it is that for large Einstein radii, the distribution is reasonably uniform as a function of Einstein radius. But then there's this big gap below about log theta e of 1.5. And then you have a few more planetary mass events below that, or planetary Einstein radii events below that. And so this gap is reminiscent of the gap that we see in the timescale distribution, and would suggest that there are two populations of objects that have very distinct mass function peaks. And so this smooth distribution at large radii, large radii would correspond to stellar mass hosts, whereas, and then there would be a break, which would suggest that the free-floating planet population peaks at smaller masses, such as at a super Earth mass. And so the one caveat in this free-floating planet discussion is that microlensing can't definitively exclude hosts for these free-floating planets. It is possible that these are not in fact free-floating, but they're simply planets on 30 AU orbits, on very wide orbits. But that can be tested with future high-resolution observations. So with EELTs, we should be able to actually answer the question of whether this population of small objects is actually free-floating or is bound to stars. And so to wrap my talk, these are the two major results from this talk. And the key here is that KMTNet's continuous coverage and very large camera is enabling us to probe new areas of planet parameter space, and in particular, these super Earth-like mass ratios and super Earth-like masses for both bound and free-floating planets. Thank you. You're muted, Robert.
Okay, I just said very nice talk.
Okay, thank you.
If as mentioned in the beginning, if you'd like to ask a question, please raise your hand using the feature. And while we let those messages come in, I've got a quick question. It might be a very basic question, but it's from one of the very first slides you actually showed. It seemed like a lot of the microlensing planets on the plot at the beginning had a very similar periodicity. Is there any specific reason for that, or is it just observation bias kind of thing?
Right. So there is an observation bias. The observation bias is that the planets are centered at the Einstein radius.
Oh, okay.
But the exact value of that varies depending on the specific event. And so, all right, I'm going to cheat now. Yeah. This is a plot that compares the microlensing planets to radial velocity and transiting planets as a function of mass and semi-major axis. And so those microlensing planets are spread out over a range of semi-major axes from like sort of 1 to 5 AU-ish.
Okay. Yeah.
But if you show a log plot where you're really emphasizing the hot Jupiters, then they get kind of smooshed.
Yeah, that's good. Yeah,
right. Like if you go farther in AU that way.
Yeah.
Yeah.
Okay. Well, thank you. We have a question from Anna. If you would like to unmute.
Yes. Hi, Jennifer. That's really exciting. Thanks for the talk. I had a question about one of the last life curves you were showing, where it seems like every location at KMNet kind of had two sets of points.
Oh, yes.
And so I was wondering, kind of where is that coming from, and how does it, I assume, improve your analysis?
Well, where that's coming from is the fact that we have two slightly offset pointings for the highest cadence fields. And so because you're dealing with different pixels and different parts of the chip, we actually analyze the two pointings separately as separate data sets. And so that's what that is. So you could do better just by continuously observing with the same pointing. It's just that we have the offset pointings there. So for photometric reasons, we analyze them separately.
Interesting. Is this the standard in the field? Has this been kind of shown to just kind of improve the accuracy and the robustness of your conclusions, having this sort of almost independent sets of
well, they're
data?
not quite independent. I think the key thing is that we don't photometrically align individual data sets. We align them using the microlensing light curve itself, and that's a more accurate way to align them. rather than say using comparison stars or something.
Very interesting. Okay, thank you.
Okay, so do we have any more questions? I don't believe there are, but that's our time actually, so that works perfectly. I will then hand over. So thank you again to Jennifer.
Right, I'm going to stop sharing. Thanks.
And I will hand over to Griffin to introduce our next speaker. Thank you.
Yeah, thanks everyone. So just a reminder, if you came in late, that this meeting is being recorded. I know Zoom already warned you, but if you don't want to show up on YouTube, then let us know or turn your video off. Our next speaker is Somayeh Khakpash. She is a postdoc at the University of Delaware right now. Somayeh received her PhD from Lehigh University under the supervision of Professor Joshua Pepper. For her dissertation, she worked on developing automatic algorithms to characterize and classify microlensing light curves. She's now a postdoctoral researcher at the University of Delaware, and in her new position, she's more focused on the data science aspect of astronomy, and is now working on using Gaussian processes to generate templates for stripped envelope supernovae. So something totally different that you can ask her about later. She's also investigating different AI approaches to classifying microlensing events and also variable stars. So Somayeh, did we manage to figure out this technical issue that we're having? No. Okay, 1 second, sorry. We're trying to allow her to share her screen.
So is Somayeh unable to share because she's not co-host?
I think so, but Somayeh, can you try it anyway?
It doesn't allow me.
Yeah.
It says host disabled participant screen sharing.
We're trying to make you a host.
Okay, well, we could just allow, just allow everyone to share. I think
That's all.
Apologies, everyone.
We thought we could do this in real time.
Yeah. So Somayeh, if you would like to try again.
Yeah, it's working.
Okay, take it away, Somayeh.
Right. Okay, can you see my screen? Awesome.
Yep.
So, all right. Hello, everyone. Thanks, Griffin, for the introduction, and thank you for inviting me to give this talk. It's my honor to be here with you. And today I want to talk about a project that has started as part of my PhD dissertation. It's an ongoing project, and this part of the project that I am going to talk to you about has been just recently published. But as I say, it's going to, there are so many other steps that need to be taken for the rest of the project. So today I'm going to talk about classifying high-cadence microlensing light curves. I will talk a little bit about microlensing in general, and then I will start talking about the idea that we had and implemented to classify high-cadence microlensing light curves. I assume Jennifer gave you some introductions. I'm just going to quickly mention some introduction to microlensing. Microlensing is a phenomenon when the light coming from a distant star is lensed by another star that is closer to us. The star in the middle is usually a cool, low-mass star. As a result of the lensing event, theoretically, we should be able to see multiple images of the distant star, but we're not able to resolve the images. So then as a result, what we see is a brightening of the source star. That would appear as a peak in the light curve. And in this animation, you can see the lens star is, we assume it's a stationary star in the middle, and then the source star is getting closer to it and then moving away. And for a single lens system, we can expect in the absence of second order effects, there's the symmetric peak that happens, the peak of it happens when the two stars are closer to each other from our point of view. And so we can assume, like in the absence of second order effects, we have the symmetric peak for a single lens event. And then, for instance, if the lens star happens to have a planet close to its Einstein ring here, then the planet we expect also leaves a signature in the light curve. so that we see the main peak that is due to the lens star, but we also see signature of the planet that could have different shapes depending on different parameters. And so here I have just a schematic example of what a planetary signature could look like. I'm not saying that this kind of shape in the light curve is common or it's like a typical planetary microlensing light curve. I'm just giving you an example of one shape of these light curves. For this project, we have mainly focused on using simulated light curves for the Raman space telescopes. I'm going to just briefly talk about the different properties of this array. The Raman space telescopes, or formerly known as WFIRST, is NASA's mission expected to be launched in 2020s. And the microlensing survey will take place during 672-day long seasons spread throughout the mission's lifetime of 5 years. And the cadence for the microlensing survey is 15 minutes for observing parts of the galactic bulge. And it is estimated that it will observe about 10 to the 8th stars, and it will discover about 54,000 microlensing events, and it's expected to find about 1,400 planets. So these numbers are important to know to so that we can raise this question and try to address that. So I'm raising a question which is basically applicable to many fields in astronomy. Given the large number of Raman and microlensing light curves, we need to have automated algorithms that can quickly look at the different types of events that we have and give us some preliminary information about what's going on in those light curves so that we can save more time and we can start like doing the full analysis on the ones that are more important to us. And for these kinds of questions nowadays in astronomy, machine learning and AI have been used more often for classifying purposes. And here, this is the approach that we want to test and see how well it works for microlensing light curves. So this whole project is sort of preparing the basics that we want to define in order to be able to test machine learning algorithms. So we want to use supervised algorithms using features that we define specifically for microlensing light curves. And we want these features to have physical meanings so that when we are using them as inputs to machine learning algorithms, we're sure that these are features that are physically important for our science case. So when we want to define these features, one thing we need to be aware of is the diverse shapes of the different shapes that we can see in the microlensing light curves. And for the Raman Space Telescope, since it has a really high cadence, we would be able to basically see so many details of these different shapes. So it's very important to consider all these different features that we see in the light curve. So here I'm just having an example of some of the simulated events that we had in our data set, showing either a single lens event or binary lens events. And the binary lens events could either be planetary systems or stellar binary systems that would cause different features. One thing to note is that these different types of features that we're seeing here are basically, they depend on parameters like, for instance, the mass ratio of the binary lens system or the path of the source through the lensing system. And that would really create so many different shapes in the light curves that would really be hard to track just by looking at them. So our idea is that we want to basically come up with features that we can calculate them, features that are computationally cheap to calculate. And we want these features to pick the different physical phenomena going on in the light curves that then we can use that information to basically know what's going on with that light curve. So here I have 6 examples of microlensing events. The first row are the the single lens events, and the second row are double lens events. And what I want to draw your attention to is to the different basically features that we want to like take from these light curves. So one thing that is easy to basically test in the beginning is to fit a single lens model, microlensing model, and see how similar that basically the peak that we have is to that model. And then using that fit, we can then determine compared to a PSPL or point source pointless function, how symmetric the peak is. And one other thing that we one other thing that we want to basically quantify in some other ways is how flat the peak of the microlensing lens is. So depending on how much the microlensing event is affected by the finite source effect, the top of the peak will be flatter. And that is because what happens is that when the finite source, the finite area of the source is comparable to the Einstein radius of the lens, then you get this smoothing effect where like the sharp features in your light curve will become smoother. And using a Cauchy distribution fit, we try to quantify that flatness of the top to see how much we can get information out of that. And then for some of the microlensing events, this flattening becomes so much strong so that the whole light curve will be different when the lens mass is much lower. For instance, if when your lens is a free-floating planet, it is more affected by the finite source effect because the Einstein radius of the lens is much smaller. And in those cases, we expect to see a single lens event that is kind of resembling a trapezoidal function. So by fitting a trapezoidal function, we basically wanted to see our ability to find these kinds of events. And we have used the idea of Chebyshev polynomial fits introduced in the literature to quantify some of the informations in the binary lens microlensing events, specifically stellar binary lens events. And I will get into more details of that. And then finally, we have tested this combination of function of a PSPL plus a BZ function. I will get into more details of what a BZ function is. We have tested that to basically trying to characterize the planetary features, the sharp perturbations that we find in microlensing light curves. So for this project, the simulated data set that we have has 4 categories, and it includes a category of single lens events, a category of events with stellar binary lenses, and a category of events with planetary systems as the lensing system. And we also have one category of non-microlensing events, which only basically includes simulated light curves of CVs, characteristic variables. And the reason at this stage we are only including CVs is that the CVs like have peaks that could resemble more the microlensing light curves and could be mistaken for that. So this is the reason we have included them at this part. And all right, so I'm just going to show you quickly what exactly these features are and how we're evaluating them. And eventually I will tell you like what is a plan to use them and what we find by just a preliminary analysis of these features. So, so as I mentioned before, by fitting a single lens model to the light curves, the single lens microlensing event model, we then define this parameter beta to find the ratio of the chi-squared of the PSPL fit to one wing compared to the other wing. And with this, we want to evaluate the symmetry of the light of the peak compared to the PSPL model. And we look at the distributions of the beta parameter for different classes of light curves in our data set. And the Cauchy distribution fit is used, it has this, the parameter B that basically defines how flat the top of the peak can be. And we use that to basically compare the peak of the light curve to PSPL model, so that if it's more affected by the finite source effect, we expect that it deviates from the PSPL model and then gets closer to the top of the Cauchy distribution fit. We define this parameter psi as a difference between the chi-squared values for the PSPL model and the Cauchy model. And we expect that we get higher values of psi when we have a strong finite source effect. What we find here, this parameter rho over U naught determines how strong the finite source effect is. If it's larger than 1, it means that the finite source ratio rho is more significant than the impact parameter, which is basically the smallest, the two objects get closer to each other from our perspective. And then we get larger numbers of psi, larger than 1, for events that are significantly affected by the finite source effect. And the Chebyshev polynomials was first introduced by Roseanne to identify binary lens microlensing light curves. This is really a neat idea. What we did was that we tested, we fitted the light curves with a 50-degree Chebyshev polynomial, and we used, we kind of like extracted some parameters from that and like tested that to see what kind of information we can get out of that. Here you can see light curve of a binary lens microlensing event. It's stellar binary lens event, which is fitted by a Chebyshev polynomials. And so one parameter that we are calculating by from the normalized coefficients of the polynomial, and then we compare the distribution of that for the different types of light curves that we have to see if that gives us information about the features we see in the peaks. And then we also look at the first 10 event coefficients as indicators of the classes. We are here plotting the 8 coefficients versus the 6 coefficients as suggested by Di Stefano in 1997. We're doing this for the different categories of the light curves that we see. We do the same for other first 10 even coefficients, and we find that there are like different distributions for distributions of these coefficients for the different categories that we have. And then finally, for focusing on the planetary system lenses, we have used this BZ function, which is basically developed to fit the spectra of galaxies. And the BZ function has the ability, if you play with the parameters, you can basically get a lot of different shapes out of it. So it resembles the double peaked perturbations of the microlensing events, and also you can get single peaked perturbations from it, but just playing with the parameters. And it was exciting to test it. So what we do, we test a PSPL plus a BZ function model to fit to the light curves, mainly the planetary system light curves, to see what sort of information it gives us by just quickly fitting this function, as opposed to fully analyzing the whole parameter space to find the best fit model. We did that for the data sets in our, for the light curves in our data set, and what we find is that it really gives us interesting information about the light curves. I will tell you in just a few seconds. I just want to emphasize that what we're doing here, we're not like trying to feed every data points in the light curves. What we're trying to do is we want to get an estimation of some of the features of that perturbation, like the duration and the amplitude, like features like that, to get a sense of what sort of events we have. So then from this fits, we estimate two physical parameters of the systems, the mass ratio and the projected separation, and we compare them with the true values that we know from the simulations. And here I'm showing you the Q, the mass ratio, and the projected separations, the fitted ones versus the true ones. What we find is that we can estimate the Q within one order of magnitude for most of the events using this method, and then we're doing much better for the projected separation. This is very important for us so that we can use this as basically sort of like telling us quickly what sort of events we're dealing with. Also, we can use these parameters as initial, as like priors when we want to fully analyze each of the systems in the future. And then, so finally, we have a list of features that we have defined specifically for different phenomena happening in the microlensing events. Now, the idea is to use these features as input to machine learning algorithms. At this point, we're not like able to fully test this, because I will mention what are the steps that we need to take in order to do that. But we've done some preliminary analysis by just assuming that if you're going to do like step-by-step scenario of classification, like classifying first between non-microlensing and microlensing, and then doing single lens versus binary lens, and then doing stellar binary versus planetary binary, and then evaluating the different subsets of the features to see how well they work on different classification scenarios. And so this is like some preliminary results that we did using a random forest classifier, just to basically see how well the features are doing for the different scenarios. And then finally, the whole idea is that we have defined these features. We know that these features contain important information. What we want to do is to do a full analysis of the different algorithms that we can use to test these features. And we have a few steps that we need to take in order to make sure that this analysis is just applicable enough to the real data. And one is that we need to include a variety of stellar variability. We're planning on doing that at this moment, and then testing different machine learning algorithms. We need to increase the number of examples in the light curves. And one other point that is also interesting is that the PSPL plus PZ function by its own is a powerful algorithm that can characterize microlensing events in such short time. So now I just finished my presentation. I can take any questions.
Thanks, Somayeh. Let's everybody give her a round of applause in the reactions menu. Does anybody have any questions for Somayeh? If so, you can raise your hand in Zoom. I'll start with one myself. This is really cool that you can use machine learning to, estimate physical parameters here, but I think it seems like, and maybe it's a naive question from someone who knows nothing about microlensing, you still need to know that there's an event there in the first place, right? Before you do any of this stuff. So how do you find that, how do you know what chunk of time to cut out and try to extract features from?
Yeah, that's a good point. So so in the classification scenario that we were thinking of, we were thinking of first finding the microlensing events from the non-microlensing events in the first place. So we were testing the different subsets of features to do the first basically type of the analysis. And it actually, the features actually work really well just in the preliminary tests for the first classification step. The problem is that at this point, we're only including the CV light curves, which is pretty much it's a good example of the light curves that could be mistaken for microlensing, but it's definitely not enough. We need to add more variety of stellar variability to make sure that this is working well. Although periodic variabilities is just easy to distinguish from microlensing events. but it's still important to include them. Was that the answer to the question? Sorry if I didn't understand it completely.
Yeah, I think so. So, okay, Jennifer says she has a question next. So go ahead, Jennifer.
Okay, yeah, so that's an interesting idea to classify things automatically and the different features by using different features. In your classification scheme, I think you said that you divide it between microlensing and then the binaries and then the single lens events, and then the binaries get subdivided into stellar events versus planetary. Is that correct?
Yeah.
I was wondering if you tried instead doing subdividing it into binary like and point lens like, since the planets are often a very small perturbation. In some ways, planetary events are more similar to point lens events than they are to binaries. And if that, as an alternate like, does that work? Is that something the algorithm can find on its own, or?
So do you mean like basically finding like dividing between single lens and binary lens, like in general, or like specifically planetary system lenses versus single lenses?
Yeah, I think if you're primarily interested in planets, then it makes sense rather than subdividing it by number of bodies, subdividing it by like light curve morphology, so that you'd have single lens like things, which would be point lenses, planets, and finite source events.
Yeah, I think we can certainly do that. I mean, what we tested so far, like we tested single lens versus binary lens in general, which wasn't really hard to find out except for like some of the examples. But we didn't do like a specific focusing on the planetary versus like the rest of them. But I think it's really doable because, as you said, like a lot of them, I mean, a significant number of them are like have like specific features, like small, sharp specific features that have their own characteristics and should not be hard to find. But there are also ones that really look like single lens events, and they would be really challenging to find out if they're basically like planetary systems. We haven't tested that, but I think it's definitely doable, like considering the process that we have defined to do this.
Okay, next we have Roseanne.
Oh, hi, that was a great talk. And you too, Jennifer. So what I wanted to comment on is that, as you very well know, because people should know, Somayeh has been playing a very key role in preparing LSST to be able to, or the Rubin Observatory to be able to detect microlensing events. So as you very well know, there's a simulation that was done, the plastic simulation, to test how well people, not necessarily astronomers, but people including data scientists, can identify events. And for that test, people developed light curves to simulate many different types of things that would interfere with lensing. For them, they were the things they were interested in, whether it was supernovae, novae, all sorts of variable stars. So I wonder if there's a way for you to access some of those simulated data, perhaps from Rick Kessler, and that would allow you to enrich your tests.
Yeah, that's actually something I've thought about it a lot. I have the simulations for the plastic challenge, and this is definitely something I'm planning to do, and that is basically evaluating the performance of the set of features on different cadences. So these are like basically like only high cadence light curves that I've been working on, but it's really interesting to know how effective each of these features will do on like lower cadence light curves. So that's definitely something I'm really interested to do.
Well, you know, Rick should have the high cadence light curves too, because people gave him well sampled light curves, and he then just put it into LSST with sampling on LSST frequencies. So he will also have the original very high cadence light curves. And some of them, like supernovae, for example, Super Macho found them to be real irritants. So it would be very nice to see what you, with your wonderful set of automated methods, find.
Yeah, that's right. Thanks for your comment.
Okay, I think we have time for one more question from Natasha.
Hi, awesome talk. I was wondering if you've thought at all about parallax and how you would go about distinguishing those effects from the ones that you're talking about.
Yeah, that's a good question. So we've thought about it. We haven't exactly tried to quantify it, but so we try to like assess the symmetry of the light curves with respect to a PSPL model. And that's a really powerful tool. It's just that we haven't exactly checked how that would work for light curves that are like single lens light curves with parallax effect versus like planetary systems that look like, you know, PSPL models would just not like asymmetric peaks. You know, we haven't tested that, but that's definitely something we need to include in this. We need to evaluate how well we can basically tell them apart.
Okay, thank you again, Somayeh, and thanks everybody for coming. There's still some slots left to sign up for one-on-one meetings with both the speakers if you are interested in talking more. And we'll see you next week.
Thank you.